Guten Abend, Berlin. It's a big pleasure for us to present this research at OffensiveCon. So, especially, it's been already a lot of talks about UEFI, but this one is special. It's targeting for the first time ARM systems. But before we started, I'm Alex Matrosov, and my colleague Alex Ermolov here. So basically, we'll be presenting this research. And this research is actually started from just for fun. We tested a few similar attack vectors which we've been using on x86 systems related to NVRAM on ARM, and suddenly it works. So this is how it started. But before we go deep to the technical details, I want to introduce binary research team, part of it which has been involved particularly in this research: Sam Tomas, Alex Ermolov, Yegor Vasilenko, and myself, Alex Matrosov. So basically, UEFI been developed kind of like in early 2000s and mostly been focused on x86, but about 5-6 years ago, when more shift start happens into the direction of ARM servers, UEFI forums start thinking how they can, actually UEFI committee, not forum, start thinking about how they can shift the same mindset around the UEFI, make it more standardized for ARM systems as well, and working in this similar manner. Actually, in this case, operating system will be communicate with the firmware in the same way. It will be less distraction from the perspective you need to adopt your operating system security for different type of bootloaders. And I think this has actually been initial push. But x86 historically been having UEFI way more longer, and in this perspective, of course, attack surface, it's been well known for 20 years. But think about like this screenshot on the middle of the slide, we copied from one of the presentation from UEFI forum. So some of the architects really believe like a solution needs to be flexible as system management mode and offer the same higher level of security. So in terms of security, it's kind of questionable, because if you think about almost from the first OffensiveCon, like 5 years in a row, I've been talking about like UEFI insecurity on this conference, so it's very secure. And also binary research been disclosing 300 plus vulnerabilities over a year related to system management from the different perspective, mainly memory corruption bugs and privilege escalations. So, but let's touch ARM perspective on UEFI. And interestingly, here we can see how actually the difference between ARM systems and ARM and x86 really reflecting here. We can see the big phase related to UEFI standard called Dixie, but the rest, it's actually not very related to UEFI or anything else similar on x86 systems, right? So basically we have the hypervisor. In theory, it should be actually isolate the memory. In the reality, it's just a resource manager. So, and UEFI in general, it's actually extending complexity of the boot process on ARM systems. Let's just go deeper from the perspective how actually we end up on this research. So I already mentioned that we tested a few bugs, but then we start thinking we need some device, and we figured out the cheapest one in the market. It's been Microsoft Windows Development Kit 2023. It's been also using Qualcomm Snapdragon 8, so which has been pretty recent SoC for experiments. And we get this one, so and start playing around. So the same chip is actually using on Surface X devices and ARM devices from Microsoft for their Surface laptops. And Interestingly, all the same attacks will be working on these devices as well. Some of these attacks are applicable not only for Microsoft devices and for many others. So basically, the vulnerabilities we'll be presenting today, they're splitting on the two categories. It is actually research tools and some weaknesses which actually help us to understand how the system behaves. The second part, it's actual vulnerabilities, but some of them related to reference code of Qualcomm and attacking the entire ecosystem, some of them specifically targeting Lenovo. So here we actually try to figure it out where we can find the actual firmware, and we start playing with different file systems because when you access an UEFI shell, you have a different file system volumes, and sometimes they have an interesting data. And basically, we figured out a lot of information from these volumes related how we can actually how trust zone structure looks like, and also a lot of different images related to the trustlets and many other cool stuff. But most interestingly, we try to actually understand how we can dump the firmware, because we don't really want to do some physical attacks on this device, because we've been really focused how we can more generically extract the firmware from the software way. And we start playing from UEFI shell with just usual tooling. So we get some, been running some commands like a dmem to understand how the physical memory is mapped. And we developed some dump.uefi. You can actually find this on our GitHub. We just uploaded today. So it's simple dumper, which is reading physical memory region from UEFI shell. And we've been successfully actually able to read the BIOS region. So BIOS region, it's logged as read-only, but you actually can read it, not modify it, which is cool. I think the similar concept is actually common on x86 systems when you have under the first 4 gigabytes in PCIe memory space, when BIOS region is mapped, you can just read it from kernel mode of operating system. But also for us, it's been very important to understand, can we actually read other regions like NVRAM and some maybe related to the trust zone, but unfortunately not. We get some exceptions, as you can see, and not all the regions are available. But what we find out afterwards in the firmware image, it is UEFI platform configuration file. And this has been very important finding, because this memory map describe all the mapping of interesting memory regions, but in the same time, it's also contain security configuration. So basically, as you can see, some of the flags are enabled, some of them disabled, but we can understand what exactly mitigations are or protections being enabled on this particular system. So another important finding, it is actual UART redirection to the physical memory when we can dump UART buffer from the memory region. And basically, we don't need to solder our UART device to the board for actually reading all this serial output information. We've just been reading from the memory. And this has been very helpful to reconstruct the whole order of the boot, different bootloaders and the whole boot sequence. So this is an actual high-level perspective how the system boots, right? So we have a mutable bootloader, which is start from the chip, then it's passing control to first level bootloader, and then later actually running trust zone and Dixie phase for UEFI on the ARM systems. But interestingly, all the structure we already reconstructed, but what actually the trust zone responsible for on the system, and how actually really hypervisor works. This has been kind of an open question for us, and it's where we actually dive deeper in our research. But also, importantly, like afterwards, we realized hypervisor, it's actually only related to resource management, like basically running some specific trustlets in the trust zone, which is related, as example, to NVRAM and some other stuff. This has been very different from x86 because x86 attack surface, it's way more simplified from the perspective of attacking NVRAM compared to ARM systems. Basically, when you need to go and have the privilege escalation or the code execution into the trust zone to actually read the NVRAM variables. And just for the people who not really familiar what the NVRAM variables stand for, so basically, let's say it's some configurational part which is related for many things on your systems. It can be security, it can be some of the functional system, or some variables related to the secure boot, and many other things. And this is specific non-volatile memory region, which is actually can be accessible in runtime, or specifically can be read and cleaned up from during the boot. It depends on the specific variables. But usually access to these variables can be protected as well. On x86 systems, Intel introduced authenticated variables, which can be read and write, actually can be read out of SMM, but modified only if you have privileges from system management mode. So here, actually NVRAM is way more different. I would say it's more protected, and attacking NVRAM is much more complicated on ARM systems. So basically, we've been thinking on NVRAM on the same way as we actually been looking on x86. This picture is applicable to x86 systems. If you think about NVRAM on ARM, just cut the platform initialization phase pre-UEFI, and then it will be exactly how it looks like on ARM. And all the services, it goes through trust zone, trustlet. Also, importantly for us, we already have some automation to understand attack surface and what kind of variables are exposed from the drivers. So our plugin, UEFI Explorer, actually providing memory map for NVRAM, and it is related for both x86 and ARM. So if you're thinking about to start some UEFI related research, so it's a very good way to actually dive into it. And here we go. This is the vulnerabilities we are discovered and disclosed. And honestly, this has been very interesting disclosure itself, because initially we've been thinking most of these vulnerabilities is platform specific for the Lenovo device, but later on we figured out some of the drivers, and some of them literally related for battery charging, but it's privileged, pretty privileged drivers, which is can expose interesting attack surfaces related to Qualcomm. And the reference code ones, it is impacting not a single vendor, as I mentioned before. Also, it can reflect on some of the systems on the Samsung, HP, Dell, Lenovo, and Microsoft. So basically, it's the ones we are tested, the firmwares, and I think it can be impact any others which is use the same board and use the UEFI firmware. This vulnerabilities is actually breaks on the two classes. Part of them, it's actual code execution with classical stack buffer overflow, and the second one, it's interesting attack vector with a memory leak from the privileged memory. Alex?
Hello. So let's continue. As Alex said, the main thought is that we use the same approach we used before, when we were researching UEFI-based firmware. This is about UEFI specifics. We used our knowledge to about the vulnerabilities which happen when NVRAM parsing is happening. And we use this to find these both classes of vulnerabilities, memleak and buffer overflows. So the first one we will be talking about is the memory leak vulnerabilities. So this is the pattern. All of them are basically the same. That's why for this example we just call the vulnerable variable like variable 1 and variable 2. So the thing is that the data size is initialized and with some value, and when the get variable is called for the first time, if in case the variable is the actual size of the variable is bigger than the requested size, the get variable will rewrite the data size with the actual size, and after this, usually the I think my mic goes down. So usually this handling requires some security wrapping. So so the data size, the status has to be checked for the errors like buffer is not sufficient or something, and then the buffer has to be reinitialized, and the data size probably may be checked for is it the normal for this kind of variable or so. So in this case, in this variable pattern, nothing of this happens. Just the next call of set variable follows, and the data buffer will be overflowed with the data from the location. The out of bound read will happening, and some part of memory will be leaked, and the leakage source is depending on the type of data buffer where it is located. It could be stack, heap, or maybe some part of the image data, static data image. So this is an example of the proof of concept that should exploit this vulnerability. It's just when here, as you can see, we are setting the vulnerability size to 124, and then set variable happening with and leaking some memory. So let's show it on the demo. Let's try to. Yeah. So as you can see, for the first run, we will be dumping all the entire NVRAM storage. This is, by the way, happening on the emulated environment, and normal sizes, normal variables. The variable content is binarily ID, and after the reset, we running the exploit that will change the size of the variable, and then dumping again, dumping the storage again. And as you can see, a lot of other data occurred, leaked from the stack, occurred inside the variable. So the second classes of vulnerabilities is stack overflows. It's exactly the same, but just the opposite. It is happening when a get variable is following the second call of the get variable is following the initial call of the get variable. So you are requesting some part of data from the variable, requesting and expecting that that the size should be something, for example, like 1 byte in this example. And if in case the actual size of the variable will be bigger than the requested, the get variable will be returning an error and data size and the actual data size. But this no error and no data size is checked, and the second call of the get variable false. This pattern will be overflowing the value buffer and writing the memory to the stack in this case. So in this, actually this vulnerability is unique because for maybe the first time we see that this actually, this vulnerability can be exploited in 10 different variants, because we have 5 variables here, and you can expect the overflow with any of it. So just change the size of the rest 4 variables after disable battery, and that's it.
Yeah, very important is vulnerability as a single bug, but actually it can be 5, right?
Yeah, 5. But yeah, this is just a single CV. So as you can see, for when we try to exploit this vulnerability on our tested device, the Windows Development Kit, we saw that the buffer that we are trying to overflow is located after the return address, so we cannot expect that the classical Stack Overflow will do something valuable here. But in case of other devices, this code pattern can be reused, as this is a common thing for UEFI industry, and so this code can be used in the other routine, which parent, which is calling this code, will be storing something more valuable data, some pointers or some other objects, valuable objects and this overflow will be influencing on the code execution later. So that's why on our device we haven't proceeded with the exploitation. And so let's see for let's check the second vulnerability, the second Stack Overflow. So here exactly the same, the data size not checked, not reinitialized, but the amount of the number of variants of exploitation this vulnerability is a lot bigger this time, because the name of the variable, as you can see, is consisting from 2 entities, is 2 like strings, is section and settings. So the section is extracted from the UEFI PIL configuration file. It is inside the DXE, inside the UEFI image, and the other part is settings. So settings has has a fixed amount of names, and that's how combining these 2 parts of the names, of the possible names, you can combine the variable name and see what's happening. So actually this is also an interesting note, because these settings, this like SPSS, ACPI, and other, actually set inside the raw data, and this on our target device, these variables weren't existing, because the configuration is already inside the UEFI image, inside this UEFI PIL configuration file. But still, this code is checking for this variable, and this creates creates a case when NVRAM, when settings in the NVRAM overriding some other settings, static data inside the some part of the UEFI image. This is very interesting, because this could create another attacking vectors. And As you may be noticed, the data size is not only not initialized after each call of the get variable in this case. It is even not initialized before the first call. That's why we get this. So memory is out of resources, so something that's only because the data size, because it wasn't initialized for the first time, they are trying to it is filled with some garbage from the stack, unknown garbage, and that's why when we are trying to create the variables, the not existing variables with a combination of these names in our test device, when we were experimenting, that's why we get this on the boot. And we decided that on some machines, on other devices, there is a possibility, and quite high a possibility, that there will be a case when the data size will be initialized with the garbage, but looking as some data size. For example, with 4 kilobytes, normal size for the variable. And in this case, the crafted variables will allow to proceed with exploitation. So then we switched to the third vulnerability. We also checked that our device contains the variable fragment of code, and here the same data size initialized before the first call of get variable, not initialized after the call when it is updated with the actual size of the variable. So also just for the note that this pattern is invoked, is executed upon the callback of the event, USB config start, USB loopback event. This is some kind of a diagnostic event, and so we try to there's a little story how we try to exploit this vulnerability on our device. So firstly, I think it is worth mentioning that in comparison to the x86 UEFI firmware, we have a bit more mitigations and protections enabled here. So SLR, as always, not available on the UEFI. DEP, on some we wrote here like plus and minus for the x86 because in some cases on some devices it is enabled, on some devices it is not. But for ARM, at the moment, all devices that we were facing with shipped with enabled DEP protection, data execution prevention. So, and also the DEP. The thing is that the DEP didn't allow us to exploit this vulnerability with like it is easy on the x86, but here when we were trying to, we have been analyzing the system memory map and look for the page or for the area which can be rewritten and on the same time which can be executable, but heap, stack, or any other areas are not executable, and we gave up. Obviously we go with the ROP, but worth mentioning, worth telling a few words about the third mitigation that we for the first time we see on the UEFI firmware. So it is about the stack canaries. The stack canaries, as you can see, the canary itself is set from the random number generator, which is inside the trust zone environment. So as you can see, the SMC instruction is called to update the variable, to update the canary. But the thing is that on this system, we saw that if you see on the code fragment on the left, we can see that that the canary will be set only for when the first call of this code fragment is occurred. So this creates a case where the stack, where the canary, where the canary value will be set only once for the single boot, and it won't be changed for other modules. So we dump two modules in dynamic to check if this is true, and this occurred to be true. As we can see, the canary weren't reinitialized when loading other modules, and two modules containing the same canary variable value. So the canary, here we can see how the canary works. Is just in the beginning of the function, some code in the beginning of the function, and the check of the canary if it is the same in the end of the function. So the thing is that we noticed that only for our particular module, only a few routines were covered with this canary checking. So a lot of other routines weren't covered with the canary. And by the way, in the firmware we found a few modules that weren't using the canary at all. So the canary usage, for some reasons, it is limited inside this firmware, and this is as we can see from the Quark's lab blog, we can see that this is quite a common maybe case for the ARM firmware.
And we tried to figure it out what the reason actually not using the canary for all the functions, and maybe it's because like SMC impacting the performance and it's just a lot of function calls, or another guess, it's being maybe like a different third parties using some mitigation differently. So
yeah. So let's go back to the exploitation of our vulnerabilities. Vulnerability. As I said before, we went for the ROP, and just it was quite an interesting case to compare how it is maybe easier or not easier in comparison to the x86. When we a year ago here at OffensiveCon we were presenting how we were roping the other vulnerabilities. So on x86, the thing is that on x86 each SMM driver contains two these code fragments. It is set jump and long jump. Every module is automatically in the build system is wrapped with these two code patterns, and these such a patterns allow to build a ROP chain easily, because you can basically construct any gadget from this. But for the ARM, for the UEFI ARM, it is not so easy, and we have to spend some time to find the proper gadgets. And here we are chaining, building the ROP with 3 gadgets. The first, they are used to call just for the demonstration, to call the routine, the output string routine, standard UEFI routine, that will write some string in our demo. And this is a routine that should be called with two arguments. And as you can see in the gadget, in our gadgets we setting the first argument into the X0 register, into the X1 goes second argument, the message, which is in our stack that we are modifying, that we are crafting it with the variable, with exploiting this vulnerability. On the x8, we're saving the routine address, the output string to call it, and as you can see, the x29 also is set with some write accessible address. That's why, because the code inside the output string, it will try to get the value from the x29 register and try to write some value into it. We don't know what is the purpose. Just didn't research it well. But here we just try to make it to give to this routine a writable address to not get the synchronous exception again, and like a seg fault, just to make everything work smoothly. And the last gadget is about infinite loop, so we just stop the boot process. Yeah. Oh, sorry. This is the proof of concept code that we wrote. We will publish it. I think it's already in public right now. Oh, sorry. So it is worth mentioning that the project UEFI Rust has been used for writing this proof of concept, and we found it like very handy and useful for writing proof of concepts and exploits. So this is also the variable that we are crafting. As you can see, we saving the first, the second, and the third gadgets. We're saving the message. We're saving the address, the random address that will be accessible, write accessible on the moment of execution, and running it. About the event. The event, as I said before, the code, the vulnerable code fragment, is used inside the callback of the event, and on our system, again, the event, we didn't find the case when the event should be invoked. Probably the code is not used on our device, and we triggered the event manually, but this vulnerability can be exploited easily on other devices where this code fragment used differently, just with not inside the event or not, or the event is used properly or something. So let's see the demo. Loading, booting, and setting the variable, rebooting to see if everything is exploited well. Loading the exploit, yes, successfully exploited. This is the message that we were saving inside the environment variable, and it is delivered into the system. Yeah, it's a survive reboot. Yeah, very important notice. Thank you. Upon every reboot, this exploitation is possible. So if you create the variable, you create the you see that the triggering of this event is possible, and upon every reboot, the triggering this vulnerability, while the variable will be existing in the environment storage, the vulnerability is triggerable. Yeah. So regarding a few words about trust zone, about the second part, which is meant to be more privileged, isolated, and to as vendors said, to implement some security features inside it that SMM has been providing, is providing, of course. So about the mitigations, that we saw that the only difference in comparison to the UEFI code, that the SLR is enabled in this in this code, and that's basically all. This is the only difference. So as you may notice, that the trust zone we told that the trust zone is divided in a few different levels. It is the monitor level, with the highest privileges, the kernel, the trust zone kernel, and the trustless, the trusted applications that we saw that for our firmware it contains 3 trusted applications for implementing different security features on this device, like storing key, managing key, encrypting, the drive, I mean hard drive, and etc. But also it is worth mentioning that these trustlets are saved, are stored as the ELF files inside the blob, inside the big block, which is formatted in the GPT. We were researching the trust zone attack surface, and we saw that actually, despite the common attack surface for the trust zone, the UEFI brought a bit more opportunities for a potential attacker. Let's say it like that. In case the potential attacker through the vulnerabilities which the UEFI standard brings, in this case, the attacker will gain the code execution at the DXE, he will be it is possible for him to call different features, functions inside the trust zone, and to test the monitor handlers, the privilege handlers inside the monitor itself, inside the handlers which are followed inside the kernel, to call the trustlets to fuel the attack surface of usual attack surface of these components. But regarding the other parts, the trust zone, the boot ROM inside the ARM, this is one of the main differences from the common UEFI with the common devices with the UEFI firmware on x86 architecture. The ARM contains the boot ROM, which, as Alex said before, loading and verifying the next part of the trusted boot chain. So, in our firmware, we saw that this next part, the primary bootloader, the extended bootloader, they are stored in as an ELF files also inside the UEFI, a big UEFI image. So, as we can see, this boot ROM is capable of parsing parsing, loading of UEFI images, and ELF images. This is kind of an attack surface, and also this boot ROM works, has maybe minimal implementation of the USB stack, and allows to enable the classic download mode for the Qualcomm devices, which is usually is noted when the mobile phones researching, while researching the mobile phones. So this is also an attack surface for the boot ROM, the USB parsing, the ELF, UEFI. And also there are some other specifics like shared memory, which we saw in the first time, shared memory between the UEFI and the trust zone, which is also an attack surface for the kernel, for the trusted kernel. And finally, about the trustlets, as I said before, they are stored as the ELF files in the GPT formats. That's why we can see that this is also an attack surface for the kernel, which allows loading these trustlets, so it is capable of also doing some parsing. And the NVRAM storage also has been some kind of maintained inside the trustlets, And in case the potential attacker will gain physical access to the device, it will be a little bit harder, but to working with the form factor of the chip inside the ARM device, but still possible. NVRAM can be modified with the physical vector. And so all of this about that besides the classical trust zone attack surface, UEFI brought a bit more capabilities for a potential attacker, and as we know, despite these NVRAM these vulnerabilities in NVRAM parsing, a year ago we have been talking about a few let's call it like the security weaknesses of architecture that described in the UEFI. So I'm talking about that every UEFI, every DXC driver, every SMM driver is using the boot services, which is located inside the system memory, not in SMRAM, and callouts are possible during the boot. And also there is some window before the SMRAM, the isolated memory for the SMM mode, will be locked, and this creates an opportunity in case the potential attacker can't code execution early enough in the boot process, even inside the DXC. He can use these disadvantages of the UEFI to get the code execution, to automatically escalate privileges just without any other vulnerabilities to the SMM mode, and to get the isolated environment. We checked this opportunity with writing a tool, a module that will hook one of the services of the boot services, which, as I already said, is stored in the system memory. We picked the locate protocol procedure, which is widely used inside any DXC or inside any SMM module, and we implemented the checking and SMRAM accessing. SMRAM is not locked at the moment of calling this locate protocol routine or not, and we checked that it is actually available for some time, and which proves this concept. So in case, as you can see, this is the SMRAM dump. SMRAM dump. You can saw it by the signature, specific signature, which is SMRAM specific inside in the beginning of this dump. So Alex, the word to you.
Thank you, Alex. So as you can see, specifically like UEFI extending attack surface on ARM systems, but also interestingly, it's more secure compared to x86 exploitation. It's more complicated, and the vectors we've been showing with NVRAM get variable. It's been actually exploited on the same manner, but with a different shell code. Like in our case, in ARM, we need to use ROP, and this is kind of like a lift the level of attacker, because on x86 it's just a classical Stack Overflow. It's very easy to exploit. I think like any concept from CTF challenges will be working pretty smoothly there. So it's just literally a classical Stack Overflow from early 2000s, and it still exists on x86 systems. Like usual time frame for patching these issues, it's like 6 to 8 months, which is ridiculous. It's just 3 lines of code for fix. So, but it is a reality. So I would say from that perspective, ARM give better security, but at the same time, vulnerabilities like that, it's cross-silicon. So basically, it's design issues in UEFI specification. And I think like audience can raise a valid question why they're not doing the sanitization and get variable, right? So it's so easy and it will be just mitigate these attack vectors. And the question is performance. So basically get variable calls like 100,000 of the times during the boot and even more when it's actually going in runtime. So, and in this sense, like accessing to NVRAM, it's required for operating system, it's required for the boot process, it's requiring for many services related to the firmware. And if we implement the mitigation there, the performance downturn, it will be about like 5 to 7%. And for modern manufacturers, which is just like fighting for milliseconds, how fast it will be blinking on your laptop, the screen on your laptop when you open in the lid. So it's unacceptable, and they basically think mitigation is not necessary in this sense, so performance is more important. It's where performance versus security, so what we can do. And this attack vector is very well known. I would say it's not new. I think novelty on this research, it's been new perspective on the ARM systems when nobody before on public didn't publish any vulnerabilities related to get variable on ARM. Second, we found a new primitive, which is actually leaking the memory related to the set variable, right? And I would say UEFI specification is great standardization, but also in many cases and aspects related to the specification been invented in early 2000s and not really modified to modern attack landscape. And if you think about like literally the most probably recent case when Black Lotus bootkit with UEFI bootloaders related need to have a hashes in DBX storage to blacklist like a vulnerable bootloaders, right? And DBX hash storage, it's just 64 kilobytes. It's a variable size. So basically, to add all the bootloaders, which is actually can expose this vulnerability, it will be run out of space of this variable. So it's impossible. Basically, when DBX storage for blacklisting in UEFI being designed, it's been just probably 1 or 2 bootloaders included, and it's been over the time, probably from 2019, they start including more and more blacklists related hashes for bootloaders. And now we don't have enough space, and adding new variable, it will be actually cause new attack surfaces with race conditions and basically replacing fake variables with DBX storage and others. This is a lot of discussions going on, but basically I would say any sort of standardization like that, it should be review it over the time from the attack surface perspective. And when we add in new silicon to support this specification, we also need to revisit from that perspective. When I've been talking with some firmware developers for ARM recently, so basically they never think such attack vectors will be work. They're more thinking from the perspective of basically existing attack surface on ARM, but not basically new one, which is UEFI bringing to the ARM world. And also, sadly, all the static analysis tools, like which is working on the source code level, finding classical like memcopy misuse and others, will be not actually finding anything related to get variable because it's actually lack of the context to the firmware, right? So this is kind of like a summary, but also I want to say ARM actually more challenging to exploit, as you can see, compared to x86, which is good. I mean, we bring in new level of security, but we need to also think more of complexity of UEFI, which is actually expanding complexity of the entire boot process on ARM systems. So, as I mentioned before, UEFI Explorer plugin for IDA Pro we developed already support ARM systems. So basically ready to use. And we will be happy to see more research coming from the UEFI perspective on ARM as well. All vulnerabilities we already added firmware hunt rules, which is basically open source tools to find known vulnerabilities. You can basically get them to understand better the triggers. And thank you so much for your attention.